PowerPoint presentation. Maraging. My name is Sivasu. I'm currently a senior research fellow at JNT. I'm pursuing my PhD full-time PhD. My research area is 3D printing, but the material that I'm working on is marine steel. I focus on specifically on the post-processing behavior. So, as part of that literature survey, I have to look for the different aspects of these material in terms of processing, post-processing, etc. So we'll be going through comprehensive overview of this particular material and conclude with some of the challenges even the additive manufacturing that this particular material is now a trending research topic for additive manufacturing. A brief outline of PPT. I will go through the introduction of this particular material, how this material is unique from other high strength steels, and then the classification of steel, where it sits in the steel family, and the other steels that are there in the industry. The concept, which is particular, the underlying mechanism, the strength mechanism of this particular material, and the grades offered from the commercial standpoint from the industry. We go through the advantages and applications, and then industrial aspect of it, in terms of the heat treatment cycles that are performed, the manufacturing process that this is subjected to, the mechanical properties offered in the machining, given the machining research and findings that we have accumulated from the inception of this particular material. And then the nitriding and corrosion resistance that is informed for enhancing the surface properties, how those findings have come up after the research that we have done. And then we'll look at the additive manufacturing in terms of how this particular material has performed in the additive manufacturing research, the different aspects, the different process parameters from the additive manufacturing process itself, and then later on post-processing behavior. So a brief overview of that particular domain, and followed by the challenges and innovation. Basically, the challenges that we have encountered so far, and from the conventional manufacturing perspective and the additive manufacturing perspective, and then the corresponding innovations that take place, and even the future challenges that are still yet to be solved, right? How the different institutions in terms of research and academia are coming up with solutions to the problems faced by the industry. We'll have a look at that as well. So, starting with introduction, what differentiates, the first unique difference that you see, that this is the high strength. So, other steels we know of that are plain carbon steel, low, medium, and high carbon steel, they are not having that strength. So, relatively, this is the high strength steel. That's the first unique thing. And this is a special steel. And it gains its high strength from the precipitation of intermetallic compounds and distinctively superior toughness. It not only does it have high strength, it does so by ensuring that toughness as well. So the material is able to have high strength along with toughness, makes it special. It is essentially carbon, almost about 0.02%. So the carbon added is very low, extremely low amount of carbon. and that's why it is said to be essentially carbon-free. We'll see a comparison of these carbon percentages that are added in the different grades of steels in the steel family in the next slide. But essentially, we can say this is a carbon-free, almost negligible amount of carbon. High amounts of alloying elements. This is one unique factor that because of the absence of carbon, we are now adding more alloying elements. We'll see why these elements, alloying elements, are added, although they are costly. Nickel of about 18%, significant share of nickel, cobalt 8 to 12, and molybdenum 5%. So a high amount of alloying elements that we see in this particular material. You have a martensitic microstructure, but the martensitic microstructure is not by high carbon. The martensitic microstructure that we see in martensitic stainless steel, for example, or other steels, it is hard because the carbon content is high. Here, we are seeing a martensitic microstructure, but this is not by high carbon content. It is by nickel addition as one of the main elements. Nickel is added as the main element, so that makes it different. And the martensite form is tough. It's not hard. So that's another difference that we see. A contrast with the conventional high strength steel, we can see that this is in the conventional high strength steel, we have carbon as an essential component. A high amount of carbon is added compared to the relatively high as compared to this steel. So that is one distinction. Another thing that they gain their high strength from the form of hard carbon monoxide. This is another contrast. And they have inferior toughness at comparable high strength. Though they are able to achieve those high strengths as the marine steel, but they are having an inferior toughness. And this toughness property is a very it's attractive to critical industries such as aerospace and tool and die industry, space industry. These properties, the demanding requirement from these industries are not fulfilled by a material which has high strength but no toughness or inferior toughness. So a high strength along with toughness is an attractive alternative to several strategic industries, which I just mentioned. So those a quick contrast with conventional high strength steels. A typical applications we see aircraft landing gear. So I mean not surprising because those industries and the particular component aircraft landing gear requires you to take loads, extreme mechanical loads, also to not break, to not have this unstable fracture propagation. So the ability to not only deliver high strength but good in toughness is something that is required in those demanding demanding applications. So aircraft landing gear is one application that we find this particular material suited to. And then we have die casting dies also. So the tool and die industry, they need aluminum casting dies, zinc casting dies. These dies require strength and toughness as well to be able to withstand those high pressures that are imperative for extrusion, different dies which I mentioned, aluminum casting, zinc casting. Even those require such properties that are offered by this particular material. Rocket motor casing in the space industry. These casings have to have high strength and even sustain those strengths at high temperatures. So the retention of properties at high temperatures and the toughness also serves as it is something that is required at in applications such as the rocket motor case. Undercarriage, this is something from the structure, it is a structural component. So even that requires these properties, strength and toughness. Of course, these are just from the strength and toughness perspective, we do have as we'll see in the course of this PPT, that it offers properties which are not comparable to the other steels, even though they're having strength, but they're not able to offer those unique and the individuality of this particular material is not just from strength and toughness perspective, but uh, it's a major thing to consider. These are major properties that sets apart this particular material from other similar high strength materials. And then, okay, steels. So we're seeing how this steel, where this steel sits in the steel family. So we know from the basics, steel is an alloy of iron and carbon. Iron is the major, uh, is the base, and you have carbon added as an alloying element. So there are other alloying elements, as you can see. We have manganese, silicon, nickel, chromium, molybdenum, vanadium, titanium, cobalt, niobium, and aluminum. These are there, but the principal alloying element is carbon. We know, and that's what the steel family. That's how the steel family started. The ability to alloy carbon with iron, so that we have a lot of applications. It serves many applications. For example, in the first of the classification, the carbon steel. This carbon steel, and from the statistics from the industry, we are having over about 90% of uh, total steel production devoted to carbon steels, meaning the carbon steels have a share of over 90% over the global steel production. Over 90% of those steels produced in any shape or form have this carbon steel, are of this carbon steel. So as I mentioned, low carbon steel, mild, which we call mild steel generally, and then medium carbon steel and high carbon steel. So these are the three carbon steels that we have, which, as I said, accounts to about over about 90%. So these are uh, we can say all over the place. But there are others, for example, alloys, wherein this particular Maraging steel sits. It's an alloys, we already discussed, has a high amount of alloying. So in alloy steels, we have varying proportions of alloys added, and these are all added for particular reasons to achieve desired properties. For example, you have weldability. If you want to improve weldability, you have to have some alloying element added. So each alloying element added improvises certain property: weldability, ductility, machinability, strength, toughness, hardenability, corrosion resistance. So these are some of the properties that we require from the application perspective, and these are improvised with certain alloying elements. We'll see, as we have already seen, what are the different alloying elements. And for example, I mean, specific to marine steel, we are adding nickel. Nickel content is high, we have seen about 18% minimum. What nickel does is it increases the hardenability and impact strength of steel. That is uh, the advantage of adding nickel. It increases the hardenability and the impact strength as well. So, an example. And the third vertical is stainless. So, stainless steel, we know this is very common. We hear in our general, this is a general application. We have more uh, components, steel components that are stainless steel, SS, we call them. And there are several types. For example, and one thing to note is in stainless steel, we have about 10.5% chromium, and that's what makes it stainless. The addition of chromium improves the corrosion and several other properties. So we have these uh, types: the ferritic stainless steel, martensitic, austenitic, duplex, precipitation hardening. So these are all types under stainless steel. And just to go over it briefly, we know that martensite steel, for example, uh, because ours is Maraging steel, also has martensite. So quick comparison of how this distinguishes from the martensite stainless steel. In that martensite stainless steel, although it's strong and tough, it is strong, it is tough, it is highly machinable as well. So one more similar characteristic. It is magnetic. It is heat treatable also. Marine steel is also heat treatable. It has a simple heat treatment cycle. But the point is, though it is strong and tough, it is relatively not strong and not tough. So it has its place in certain applications. No doubt, this is used in many applications as more applicants to cater to, but has limited competence. So that's a comparison with martensite. Duplex stainless steel, you have ferrite and austenite both. It's a duplex. That's what it means, dual phase. And this is twice as strong as austenite or ferrite. The austenitic and ferritic stainless. Precipitation hardening stainless. Uh, these also possess ultra high strength because of the precipitation hardening mechanism. And the noteworthy feature here is precipitation hardening is also the mechanism, the underlying mechanism of maraging steel. Maraging steel also uh, relies on precipitation hardening to gain its high strength, although there is intermetallic precipitation going on. Uh, and so it is similar, but the high strength that is achieved along with high toughness is something that is that that gives the uniqueness to the marine steel. So precipitation hardening stainless steels are also, we'll see a comparison of how marine steel compares with other precipitation hardening steels. Uh, and in the last category, we have tool steels. Tool steels, we have about 0.5 to 1.5% carbon. So that's the amount of carbon, the range of carbon that we have. It does have high hardness, it has strength, and the applications are tools and dies. Basically, cutting tools, drilling tools. You have to have more hardness because they have to endure that high speed of the machining or drilling, etc. So a high hardness is needed and strength is needed. So that's why more carbon is added. So you see, carbon is seen as something which adds strength to all these steels. But the omission of carbon will naturally reduce the strength. So a logical next step would be to add some more elements, alloying elements, which gives the material its strength to some heat treatment. And that's what we'll see is the concept of marine. So comparing it with other conditions, what other steels do we have that compare with the strength that we have with marine? H11 steel, D6 is AC steel, AI Site 4340410 stainless steel, AM355 stainless steel. These are all there. They are having comparable strengths, but they don't compete well with toughness and other properties. Uh, you can see, as I mentioned here, limitations with conventional high strength steels. The first thing to note is pore toughness, and which I highlight. They have pore toughness and high temperature austenizing step, drastic quench. These steels require a quench process. Once they are formed, uh, the the process of bringing it to room temperature requires a quench. So that is one another distinguishing. Whereas with marine steel, we don't require the drastic quench. We have air quenching that we can do. Air cooling is preferable and has been proved satisfactory to achieve the strength and all those other requirements from the application perspective. Workability issues. These steels, although they, as I said, offer high strength, they're not workable in sense of cold working or hot working or welding even. So all these things, even some other forming operations. So workability, that's what we interestingly club it together as workability is an issue with these steels. They work harder. That's the drawback. You have welding issue because of high amount of carbon added, more cracking and issues thereof. Corrosion issues as well. So these are the problems with these steel. High strength steel, yes, but some limitations. Well, many, yeah. So we'll see. Uh, so a quick comparison with the conventional marine steel that we have. We have carbon emitted, right? This is a carbon emitted steel. So that makes it unique. Unique carbon emitted tool steel alloy. So that's what we can phrase it as. One of the keywords is this is unique carbon emitted tool steel alloy. It has high toughness, ductility, and even impact strength. So that makes it attractive. It is attractive to applications, which I mentioned, strategic applications. So that's what differentiates it. Other streams, we have minimum 0.4% carbon, which we have just seen. But we discussed essentially the carbon, right? 0.0% or less. So that's another distinction. And marine steel hardening without quenching. So they are hardening without quenching. They are hardening, but they require some quench cycles, which may induce cracking and other such issues, which may uh, influence not only the properties upon service, but during service, and the later on issues may come up. Unpredicted behavior may be seen because of such quench quenching. Quenching has an influence. The manufacturing cycle has an influence on the properties and the service condition, etc. Hardness and wear resistance is sufficient for many tooling applications. So the hardness and wear resistance that we get with marine steel has found to be sufficient for those applications. For example, many tooling applications. So even from the tool and die perspective, which I'll be speaking on much about, this steel has unique offerings. This image that we are seeing here is taken from a paper. I mentioned the references slide. What we can notice here is we see that this is the graph ultimate tensile strength versus elongation. So we can see the marine steels sit at the very extreme point of this is why this is ultra high strength steel. The elongation is low, yes, agreed. But the toughness is more. It uh, it has other properties. So, a remarkable thing is these marine steels, as you can see, precipitation hardening steels also, they're able to achieve those high strengths. So other steels duplex, DP is duplex phase steel, single phase ferrite, austenitic stainless steel. They do have high elongation. They have more of other characteristics, such as ductility and all. But the strength offered is limited. They have limited competence. That's it. Maraging steel, as we are seeing, there are different 300 and M300, which we generally refer to as, is having that high strength along with other precision hardening steels. But as we'll see in the course of this PPT, the different properties, the different comparisons in terms of corrosion, machining, and the heat treatment advantage that we get, workability, these are all added benefits and apart from the high strength. So, and there are other custom steels as well. Coming to the concept, what we have seen is this material, the development of this material started in about late 1950s at Inku Research Laboratory. This is a laboratory which was the pioneer getting the material to the market or to the industrial landscape. What they saw, the industrial benefit that this was, uh, the impact that it had last failure we can call it, in the industry was that we were able to achieve high strengths, extraordinarily high strengths, by converting a tough martin from a tough martin side. We're able to have such high strength and toughness. So, and this was very uh, readily heat treatable. Heat treatment, simple heat treatment cycle was another advantage that that had presented as a unique factor to the industry. So you have an outstandingly tough martin side, strengthened rapidly to extraordinarily high levels. The strength achieved is rapid, doesn't take much or more heat treatment cycles or a complicated heat treatment cycle. And so we can, this is a concise and objective way of looking at how this strength achieves, the strength it achieves. You have an iron-nickel martensite, which is having low carbon and which is soft. That's the way I see it. It is an iron-nickel martensite. We know the martensite matrix is not iron carbon, it is iron martensite. I'm sorry, iron nickel martensite. And it is having low carbon and it is soft. This, when age hardened with the help of substitution elements, is what transforms this material from soft to this high strength and toughness material. So that's the concept of the material. And the interesting thing is the name of the material itself hints at the three processes involved. So you have martensitic transformation and then subsequent age hardening done through aging heat treatment. So Maraging. So the name kept itself has the hints of the key processes involved in that. So that's the those are the key processes involved, and that's what gets the material to stay. You have strain-induced precipitation hardening, right? There is precipitation hardening, but there is a strain involved. In so much as the intermetallic precipitates that are developed, they have to sit in the martensite matrix. But there is good structure between these intermetallic compounds which are formed in the aging heat treatment and the martensitic microstructure that is there already. So a good structural fit ensures that there is not much strain. It is strain, but there is not much to the extent that it distorts the material upon heat treatment. So the distortion issues are also very less. Another advantage because of the fact that and the thing is the underlying thing is the precipitate uh, lattice is comparable. The lattice size of the precipitate is comparable to the lattice size of the martensite lattice. So there's not much to uh, there are not much issues in this strengthening, if we can call it that way. So that is one thing, and it is coherent and ordered precipitate phase. The precipitate phase so formed is coherent and it is ordered. So you don't have random stress points, and the strength is uniform because of the thing that this is a coherent and ordered. But the precipitate phase is coherent and ordered. Plus, there is absence of carbon. So that is what is the two reasons for this little matrix distortion quality that is material. This is hardened by metallurgical reaction that does not involve carbon. As we have discussed, the metallurgical reaction does not involve carbon. Of course, this is in comparison to the steel family, wherein you have much of carbon involved, and carbon being uh, having an influence of strengthening the strength strengthening basically in the strengthening mechanisms involve carbon in almost virtually every type of steel apart from the reasons. So that thing, and The BCC, the Martensite matrix is having BCC phase, body centered cube, and the intermetallic slope forms are nano size. To name a few, there are reciprocates such as Ni3MO, Ni3Pi, basically compounds of nickel that we have here. These are intermetallic compounds, and there is even Fe2MO. All of these, when the material is loaded, mechanically loaded, you have dislocation being prevented because of these intermetallic compounds. So the prevention of dislocation is because of these intermetallic compounds which form, and that's what gives the material its hardness and toughness. You have unique physical methods and the properties, in so much as we know that the structure influences the properties. So the structure itself, from the composition that we have, is unique, and the properties are unique corresponding. And not unexpectedly, many commercial advantages. So this unique metallurgy and properties, when the material designers and the structural designers, material engineers, they they try to exploit these the different unique properties that this material has to offer, and the many applications are witness. I mean, they they give us this idea of what these commercial advantages and applications mean. The different grades itself testify to the advantages that this material has to offer. Another thing is it is damage resistant. It can take high impact and high impact loads and shocks also. So even in the for the applications such as aircraft landing gear, wherein sudden loads that the material has to endure, for that for those specific industries, damage resistance is also high from this particular material. That property is high. As mentioned, attracted by material engineers and structural designers of these industries, aerospace, tool and die, nuclear and defense industries also. So strategic industries, because the properties are critical, they require those property retention at high temperatures, and these are all high reliability industries. They need improved performance, they need reliable performance. So the material should be able to sustain those properties in service. There should not be unpredictable behavior from the material. That's why the factor of safety is kept high in these industries. That's why they are termed to be high reliability industries. And those industries are to be served, I would say, with these kinds of material and the unique offerings from the material best suit for these industries. Coming to the different grades, uh, this material has been offered. The material, the data that is taken is from INCO document. There are several sources that have taken, but majorly have taken information from INCO research document, which are the pioneers of this development of the material. And even another document from NASA, they have given this document on the metallurgy applications of this material, very comprehensive document from technical aspects and the different dimensions that this material is subjected to, and the processing history, the heat treatment. So from that material, what they said was that the special steel manufacturers, they offer the steel in two modes, wrought mode and cast mode, 4 watt commercial grades and one cast grade. And this is generally supplied in the annealed and scale condition uh, because it is very tough in that particular state. It is soft as well. Hardness is about 30 to 35 HRs. So it is soft and tough, and correspondingly readily machined and formed. So this is the general state that suppliers supply the material in. You have, if you can see that there are different grades here. So the different grades or composition regions are there in order to provide different combination properties. So why the grades? Because you need an optimal combination of properties suited to specific application. That's why the different grades. And you can see here that we have the different types, the four different broad grades and the cast grade. Different conventions, for example, 18 nickel 1400, 18 nickel 1700, 18 nickel 1900, 18 nickel 2400, and then the cast grade. But the most common is 18 nickel 1900 in the tool and die industry. For the aerospace industry, in the aircraft industry, we have 18 nickel 250, which I hope is this one here, 18 nickel 17, yes. So 18 nickel 200, 250, 300, 350, that's correct. And the reason for different convention is different countries have different conventions. In the US, they denote it as 18 nickel 300. This is from Europe, I hope. So regardless, the lower number after nickel, the point here to note is the lower number after nickel indicates the 0.2% proof stress value for various strength levels. So the strength level, that's what it indicates after nickel, is the strength level, either in KSI or Newton per mm square, basically megapascal, different units. But the point is, it indicates 0.2% proof stress. They are available as billet, bars, rods, plates, sheets, customized forgings. These are all general offerings. The different shapes or geometries that this material is offered from the commercial industry are such and such. But what we can see here is this is the composition in terms of weight, nominal composition. You have nickel, cobalt, molybdenum, as we mentioned, major share. Titanium and aluminum also have. Nickel, what we can see is almost 18%, virtually 18%, not very much. Cobalt and molybdenum and even titanium are varied in chemical composition. So, and these are varied to achieve different grades, isn't it? We can see that these are all different uh, composition percentages for different grades. And these are designed to develop high proof stress with optimum toughness for the various strength levels. So depends how much toughness do you want. That's what gets you to picking a particular steel, because each grade has to offer certain toughness and strength. So that is to be taken as per application. It is extremely composition sensitive because in the aging cycle, for example, when the material is aged, this is sent to an aging treatment, as we see in the heat treatment slide. What happens in aging is the research findings is that there is swift aging response, and from this from an intuitive response would be this is good. Swift aging response is good, but if there is a non-optimal uh, combination, for example, the composition is not as per the specification, there is major deviation. That's not minor, but somewhat more, or even slightly in this case, because it's composition sensitive. Any change from the set range of alloys will bring about issues in the aging response. The strength achieved will not be as per the guidelines laid out or the what happens is if the composition is set to be so and so, then the strength achieved is so much. So that will not happen. That's what we mean by composition sensitive. And this steel is extremely composition sensitive. Desired set of mechanical properties. Any application, any application engineer will have a desired set of mechanical properties for an application. But if there is non-optimal chemical composition, you will not be able to achieve it for composition sensitive materials. And this is one of them. So that's one limitation you can call it. So another thing is the reason for adding all these alloying elements. A major objective is to have a high martensite start temperature, MS temperature we call it. A high martensite start temperature is desirable because there should be complete transformation of martensite to complete transformation of yes martensite to the lab martensite should completely transform to intermetallic precipitates. I mean, for that process to take place and not much distortion, these are all things that are to be ensured. Now, for all these things, the effect is, I mean, the major overriding thing is the martensite start temperature has to be high. That is achieved, that is kept as an objective when adding these alloying elements. So that is one thing to note. Nickel, molybdenum, and titanium are to be maintained for an adequately high MS temperature. Nickel, molybdenum, and titanium, these three are set for achieving an adequately high MS temperature. Cobalt, on the other hand, it doesn't directly contribute to this increasing of martensite temperature or the strengthening mechanism. But what it does, it is added to compensate for the excess use of these things, excess use of nickel, molybdenum, and titanium. And the overriding contribution is it doesn't allow the molybdenum to dissolve in the matrix. And what will that do? This will now make molybdenum available for intermetallic precipitates to form. So cobalt has an indirect contribution, is my point. The intermetallic compound that is formed by molybdenum is nickel 3 molybdenum, Ni3 molybdenum. So, and of course, this has an effect in strengthening. So the more the Ni3MO is formed, the more the strength. So that is ensured by maintaining cobalt in optimal levels. So that is the contribution of cobalt. And we can say this is a synergistic effect with molybdenum that cobalt achieves in maintaining the required MS temperature for lab martensite formation. Lab martensite is what we call that we have in the starting of the aging. Another thing cobalt does is it retards the reversion from martensite to austenite. So you don't want austenite reversion, as we'll see in the course of this PPT. That austenite reversion is an issue that is to be avoided for maraging. So even cobalt retards this reversion of martensite to austenite. Another thing is 18% nickel is critical, as I highlighted in the initial part of the slide. That nickel is not very much. Its portion is the same, 18%, and it is critical. Why? Because it heavily lowers martensite start temperature. The start temperature of martensite is heavily lowered because of it. And we have discussed that the objective is to have a high MS temperature. That's why nickel is critical. We'll see. In fact, the NASA document is specifically devoted to 18% nickel maraging steels. There are several other maraging steels, for example, 20, 25% even. But 18% is very common because it serves a lot of industries and it serves so industries because of the strength and toughness that it can offer. So 18% is the critical value of that nickel. Firstly, it heavily lowers metal side starting pressure we discussed. It retains the austenite as well and avoids complete transformation to martensite. So lap martensite replaced by twin martensite. This is another issue. Martensite that is formed should be lap martensite, which is desired. Twin martensite is not desired. And this twin martensite will be formed when this nickel percent is good. So that is another thing. It retains austenite in the sense any change to the 18% retains the austenite. That's the point. So you have to have this 18% critical again for this austenite to not be retained issue uh, and avoids complete transformation to martensite. And aluminum, which you can see, 0.1% virgin. So up to 1%, up to 0.1% aluminum slightly increases the martensite temperature. After 0.1%, it tends to decrease the martensite start temperature. So that's where uh, the aluminum is kept to 0.1% generally. Coming to the advantages that this steel has to offer, it offers high strength mechanical properties. From the mechanical properties perspective, it offers high strength, we discussed. A high strength to weight ratio as well. This is another significant feature for industries such as aerospace. They are fuel efficient, and fuel efficiency demands high strength to weight components. And marine steel offers that, and that's how it has been able to serve those industries quite well. Notch strength is also high. And this is important for impact applications. Those which have to endure such impact load, you have to have high notch strength. In terms of high strength, it doesn't it doesn't just have high tensile strength. It has high compressive strength. It has high yield strength, ultimate tensile strength, fatigue strength also. So it is high in all these aspects. And high compressive strength is desirable for tool and die industry. Just to as a side point, maintains high strength up to at least 350 degrees Celsius. So which I mentioned, property intention. Properties have to be retained at high temperatures, moderately high temperatures. So that retention is also another advantage that this material. High impact toughness and plane strain fracture toughness. But toughness properties comes into play, and which I explained why needed in so and so industries. Another thing, hardness retention is, for example, for dyes, it avoids washing away of the material. When the material is at a high temperature, it is soft, and it is therefore there's a tendency to wash off for the material to wash off uh, because of the form components. The material may wash off, so that thing is there when the properties are not retained at those high temperatures. So high hardness retention, I'm sorry, hardness retention at those high temperatures avoids washing and heat checking after elevated high temperatures. Once they are exposed to high temperatures, there is an issue of washing and heat checking also. The cracks, integrated cracks which are developed in the material of the dye will have an effect and influence on the formed components which are used, which are being formed from this dye. Processing and fabrication chemistries. Uh, from the fabrication perspective also, this is advantages from the fabrication perspective. Processing and fabrication. Rod grades are amenable to hot and cold wave pollution. Work hardening is not much, which we discussed. It is hardenable, it is workability by motion. Work hardening rates are low, I mentioned. And it is readily formed in a sense of hot form. I mean, hot working is done, cold working is done, warm working is done. And this is done without in process. So what generally happens is you have hot working being done, cold working being done, but at every step of this cold working cycle or hot working cycle, you have to have annealing process to relieve the residual stresses. This relief of the single stresses requires some in-process amines. One process, one hard-working process, and the hard-working process. You have to have an in-process amine to get back the material to get back the material to a soft state, essentially. So that thing is not required. In-process annealing is not required for this particular material. This can be worked one after the other, uh, and that's what gets this material to be called readily formed material. You have excellent weldability either in the annealed or aged condition. So you see, even once the material is, we'll see in the heat treatment cycle, it has annealing, solution treatment, aging treatment. So once the solution treatment is done and the aging treatment is done, if you want to have some welds later on, the individual components will be welded. Now these welds also have to be the increment of strength for these welds requires aging treatment. Now for that thing, it is I'm sorry, the aging process once it is done, or the welding process once it is done, uh, aging. If for example, after aging it has high strength. Now this high strength will bring about issues when it is welded for carbon steels. I mean, steels having high carbon, but that issue is omitted or is bypassed because of the omission of carbon, and that's what gets them to be called weldable even in high strength state. Another advantage from that in the comparison of similar strength materials, preheat is not required. So in welding, generally preheat is done to avoid cracking issues, etc. Preheat is not required. Another distinguishing feature, and pre-weld and post-weld treatments are also not required when it comes to welding. Once it is post-weld, I mean once it is welded, for some materials they require to have this post-welding operation being done. But and for example, in the rocket motor casings, what they did was individual rocket motor cases they had made, and once they, because this was a very long casing, rocket motor casing, so they made it in parts. They attached them. I mean, they kept them side by side and they welded. So a case study wherein they could even uh, age uh, the welded part. So just the welded part they were able to age with some special devices kept at those welds. And of course, the nearby parent material will also get aged. So even repair weldability. So this is another aspect that comes from the service point of view, maintenance point. So even to those engineers, the repair weldability that is offered by easy reworking or retreat a secondary to another maintenance and service operations. Okay? That for secondary to life, you have to have this reworking, retreating being done. It is easy for this material as per the literature from the technical documents and the research that have come up after this feedback from the service personnel and the industry uh, in which this material is applied. You have this easy reworking or retreat. Polishability is also that is another side point. Uh, Good machinability. This is something we utilized a lot, as we'll see in the machining uh, slide. Stability is also. When it comes to heat treatment perspective, it has a simple heat treatment in the sense that no quenching is involved. Firstly, and the heat treatment is very simple. You have, we'll see in the coming slide, you have a certain temperature and a certain time, and which is very uh, nominal, 3 to 5 hours for aging. And solution treatment, 1 to 2 hours. So that is what gives this simple heat treatment benefit. for this material. You have no quenching required. Once it is solution treated or aging treated, you quench it through air cooling and not water quenching, any other oil quenching. Softened in solution treated by air cooling, as mentioned, 820 to 900 degrees centigrade is the range for solution treatment, but no drastic quench. It is hardened and strengthened by aging at 450 to 500. This is the general range of aging heat treatment. Simple, as we can see. And the time is, as I mentioned, 1 hour, 3 hours, and 5 hours, 6 hours also, and 12 hours. But there is reversion of austenite issue. So generally it's kept to 5 hours or 6 hours. No decarbonization because of less amount of carbon, extremely low amount. So carbonization issue with heat treatment. So the heat treatment also, for example, the carbonization of the material will cause effects in the later on service or even the from the processing perspective in the heat treatment mode. Carbonization will give issues. So there's no carbonization or no decarbonization effects are a significant thing to note. Dimensional changes during age hardening are very small. Distortion, which we mentioned, the distortion is very low and it is predictable. There is uniform, predictable shrinkage. It is there, the shrinkage is there, but it is first thing it's uniform, it's predictable. So that makes it easy to control from the operation perspective. And another thing with this dimension change advantage is that it is possible to finish machine before hardening. So if you want to finish machining in the sense of dimensions, we have kept tolerances and for the application, from the application perspective, uh, the, the design specifications are set. So these can be met even in the before aging stage. Because once it is aged, generally after heat treatment, many materials will distort. There is a change of dimensions, either shrinkage or expansion, whatever the mode may be. But there is some change of dimensions. So that is not an issue with this material because it is predictable and then it is not much cost. So you can finish machining before aging peak. And this is there are research papers which have seen that both after aging, I mean machining is an after aging for tight tolerances, for tight application requisites from these particular industries. You can have uh, those post processing in terms of post machining being done. But for general applications, for applications which require which have this tolerance, some tolerance range to bear that can be there. This is a useful uh, feature that can be utilized. So the dimensional change is a significant aspect that has been exploited in aging heat treatment mode. They can be surface hardened by nitride. We'll see a slide of nitride. So the surface hardening through nitriding is done to improvise the wear, fatigue, and corrosion properties, etc. So they can be surface hardened. They are amenable. They are they are friendly. Nitriding friendly. Uh, in speaking of the dimensional change, there is a case study of this plastic compression transfer mode wherein for 480 degrees centigrade for 4 hours, this was the aging heat treatment schedule, and the shrinkage was 0.02 mm per mm. That was the shrinkage. So you can see very less shrinkage. And the amazing thing was this was the only material that could offer such shrinkage. So in some cases, this turns out to be the only material that can offer such properties or such characteristics. So unique characteristics and sometimes the only available material to resort to in that sense. In other cases, you have certain other high strength steels that you can take, which are cost friendly, cost competitive in the sense. But then you have to uh, manage the toughness uh, absence in that sense with those high strength but low toughness. Uh, Coming to the applications, we can see a lot of applications in various industries. You have aerospace industry, as you mentioned, rocket motor casings, landing gear, jet engine shaft also a very critical component to have. And even the drive shafts, helicopter flexible drive shafts also are made in hydrospace, marine, basically marine. You have pressure hull recovery devices, military bridges, especially portable military bridges are made with this material because of the strength to weight ratio, the strength and toughness required, the ability to carry it from here from one place to another requires them to have this uh, low strength to weight ratio. Sorry, high strength to weight ratio. Cannon recoil springs also because they require impact loads that it take. The toughness and strength even comes as requirement. Production tools. This is something from the tool and die industry that for molds, for die casting, dies, aluminum and zinc, which I mentioned, gears and machine tools. These are all applications from the tool and die perspective. Uh, the excellent properties, the excellent mechanical properties that these steel have to offer have led to longer lives, longer die lives. For example, a case study up to about 25 times more than typical die steel. The other comparable die steel, when compared with this one, this was able to offer in one case 25 times more uh, life, die life. And this we can say it makes up for the higher costs, in so much as uh, look, you can see it from this perspective that do you want the higher initial investment of marine steel as a tool steel alloy and avoid the additional delays and expenses because of the usage of low alloy steel alloy. I'm sorry, low alloy steel. So there is an offset, the cost offset. Either you spend early on or you spend later on. So, but another thing on top of that is the properties offered are unique. Not only the cost that you are kind of balancing the cost, the point wherein you spend the cost. Either the die breaks. It is a low alloy steel, high strength die, let's say. But it breaks because of some unstable fracture that is propagated, some unpredictable failure that has happened, corrosion in hydrogen embrittlement, some other issue. Now there will be delays in the production schedule and there will be additional expenses. So this will reflect on your productivity. So this is why I said it makes up for the higher costs. Marine makes up for the higher cost in the sense that it is able to offer more timeline and the delays, the, the avoiding of the additional delays and expenses and the logistics, the R&D that goes in improvise that particular issues in the production. In terms of the applications for the production tools, we have aluminum die casting die, cores also, core pins also. These are all from that document, NASA document, that they had highlighted all these use cases. Cores, core pins, these are all, they require high temperature environments and therefore require a material which can sustain those properties at high temperature, along with having more life in the sense of life the corrosion resistance, etc. Extrusion tools, dies, manuals, ramps, high extrusion ratios. So these require high compressive strength. And as we have mentioned, high compressive strength uh, is the advantage that we have. So that comes into this high extrusion ratio that we are able to achieve. Pressures and temperatures, even high temperatures, high pressures, these are all there. These are all demands from the extrusion tools uh, perspective. So broaches, even cold forming punches using cold impact extrusion of aluminum. So impact extrusion, they require impact property, and that requires toughness. So even from that analogy, we can see that the cold impact extrusion of aluminum is also is suited. The Maraging steel is suited for that application. Fitting and corrosion resistance is superior to common tools. So this is from just comparing the tool steels. The fitting and corrosion resistance offered by Maraging steel is superior. We'll see the corrosion resistance slide. So just to mention here in the production tools application, you have low coefficient of expansion from the for this material, and this minimizes heat checking. Heat checking, as we know, is this intricate web of uh, cracks that develop over time because of the thermal processing. And the more these heat checking is, uh, the more this heat checking issue, the more the surface repetition on the part produced. This die will be making some component, and the surface of the die or the profile, surface profile, or the deviation of the surface, it reflects on the components being produced in the die. So that's where the speed checking issue has to be uh, controlled, and how do you ensure that heat checking is not there. With this material, because of the low coefficient of expansion, they minimize this heat. So another advantage from the for the tool and die industry. Automobile drive shaft, gearbox, connecting rod, basically high performance material. Wherever high performance is required, strength and toughness, high strength, good toughness. You have applications in automobile as well. Nuclear also, nuclear enrichment rotors. These are also having an application for the resistance. Heat treatment, from the heat treatment perspective, as you mentioned, is having simple heat treatment cycle. Solution treatment is performed at 820 generally for complete recrystallization of hot work structure. So basically, hot work is done, as I mentioned. This has an influence on the microstructure. So now you have to bring back this microstructure, this distorted microstructure, work hardened microstructure to austenitic, fully austenitic, which is soft, and therefore ready for further hard working, cold working, any other form of working that you want to do in the the working schedule. I mean the production schedule of the component. So this fully austenitic structure is achieved after solution heating. So that is done. While it is formed, while this material is formed in the manufacturing perspective, you have this material taken from FCC austenite to BCC martensite. That is what is happening. Face-centered cubic martensite, or sorry, face-centered cubic austenite to body-centered cubic martensite. So that is when it is being fabricated in the first go. But once it is casted or hot, then you have some hot working to be done based on the application requirement, basically the geometrical requirement that you have to bring it to some geometry. You have some processes to be done. Those processes require in-process annealing, which we mentioned. Those, if you want to achieve in even, I'm sorry, not in-process annealing. Once it is formed, as in the final structure is made, final geometry is achieved, and then you have to go for aging. This is not done. You have solution treatment as a step. Solution treatment is done to ensure that the microneedling is completely austenitic, and then you go for it because you want to transform complete austenite to complete martensite. That is the principle. So that thing, and another thing is extremely low amount of this carbon, low percentage of carbon. This for this because of this advantage, a, a protective atmosphere is not required during anything or even aging, and the cooling rate is not critical for marine instance. The cooling rate is not critical; it doesn't need to be controlled. So you have this advantage as well. Air cooling is done, but if you don't have to control the air cooling, uh, that advantage for both solution and aging. Aging treatment is done at 480 for 3 hours, and the variations are there in temperature and time duration. As I mentioned, 1 hour, 2 hours, 30 minutes also is done for aging. 30 minutes, 1 hour, 2 hours, 3 hours, 5 hours, or 6 hours. Temperature is also there from 450 to 500, 550 even sometimes. That these are there to achieve the different grades and corresponding strength achievement levels, and which we mentioned. You want to have certain strengths, so that will those are controlled with aging schedule, aging heat treatment, time and temperatures, etc. Air cooling is done, as I mentioned, for both heat treatments. Air cooling is sufficient. It ensures sufficient cooling rate and doesn't need to be water cooled or water quenched or oil quenched because it ensures adequate quenching rate to reduce complete transformation of matters throughout the heavier section, even the heavier section, not just thinner section. Sections having moderately high or higher thicknesses, you have air cooling is sufficient there even. Undesired transformations are prevented even at a relatively slow cooling. Even if the cooling rate is very slow, there is no transform, there is no undesired transformation. For example, it doesn't transform, martensite doesn't transform to, I'm sorry, austenite doesn't transform to bainite or pearlite or ferrite. It transforms to, say, martensite. So that advantage of not going to this undesired transformation is another aspect. Also aging, this is also performed, but this is not generally performed, wherein you have the aging of the austenitic matter. Basically. What you do is you interrupt the cooling cycle from the 820. Once it is taken from 820 to down, it is interrupted at 510 to 6, and it is held for several hours at that particular temperature prior to cooling again room temperature. So this halting and holding is what uh, is a significant feature of osage process. And then later on, it is subsequently aged, which imparts its higher strength, slightly having slightly higher strength compared to the normal STD cycle, solution treatment aging cycle. This all aging osage is able to have higher strength. So specific purposes, this may be utilized. Osaging and dimensional stability, which we have discussed already. Overaging is at both high temperatures or high time, it leads to higher than normal. So overaging is something that is not desired. Aging schedule has to be set so that austenite diversion is not there, and this shrinkage issue is also not there. Second point is that absence of retained austenite, it ensures more dimensional control even during service. Not just from the perspective of softening, but even from the perspective of service. In the service also, retention of austenite comes off as an issue. So this is something repeatedly seen in the research papers, that they see how much of austenite is retained. And we can start to have an understanding of why this is an issue, or is it an issue, and then why it is an issue. So dimensional stability ensures, requires or entails that austenite should not be retained, or should not be reverted. There should be no reversion of austenite. And even during overaging, softening occurs. Softening is not required. We will not design because it will reduce it. So that is not recommended. Austenitic reversion. This is kind of a twofold. It is interlinked. Overaging leads to softening and austenite reversion. There are interlinked aspects. A modified aging cycle is instead for die casting applications for increased die length. So there should be some modification in the aging cycle if you want to increase the die length. So industries which are interested, they go for this modified aging cycle in order to be able to closely control what properties that they want for that particular application. Basically, two deadlines, and you have uniform heat treatment as another beneficial aspect of this material. That the heat treatment is uniform. It is not as in the material is uh, uh, strengthening in one area and not strengthening in the other. There is uniform heat treatment response, and this is another way to see it. Uh, Non-distortion advantage. That it doesn't distort because of this, because it is uniformly responding to the heat treatment cycle.